Okay, last one on goodness of fit. Let's see. For reasons known only to social scientists, the General Social Survey regularly asks subjects their astrological sign. Here are the counts for them. Okay, if births are spread uniformly across the year, we expect all 12 signs to be equally likely. Are they? So we're gonna. Um, so, well, are these equally? Well, they're all. I mean, they're close, but they're not. Well, not really close actually. 400 and 331 and so forth. Um, okay, so we want to know if this distribution right here is significantly far off a uniform distribution. A uniform distribution meaning all of these are exactly the same. Okay, does that make sense? So if they, in other words, is it likely to get a distribution like this if all of these are uniform? If they all should be the same? Okay, so let's check and see. So H0 would be um, the distribution of signs is uniform. In other words, uniform meaning the same. Okay, HA, the distribution of signs is not. Okay, and so is this evidence, is this that it's clearly they're not all the same? Is this far enough away from them all being the same for me to go scratch my head and go, I don't think the distribution could be uniform, because if it was, I just wouldn't get this distribution. It's just not likely. Okay, so the conditions. Okay, random or representative sample. Okay, so we're going to assume that. The data has to be counts, and the expected counts have to be greater than 5, which we'll see in the course of our problem, if that is the case. Okay, well the question is what's our sample size here? We have to add all those up. Okay, 321 plus 360 plus 367. Oops, I'm going to pause it and just do this. Okay, I've got n is 4024, as long as I added these right. And now I have to figure out what's the expected count for each of these. Well, since I have 12 signs, and I want to know what, of the 424, if they were divided evenly, what percent do they each get of this? If I divide that by 12, okay, sorry about that. If 4024, I can divide that by 12 to figure out how much each month should get, or I know that it's 12 months, 100 divided by 12 is 8.333%. So I can do it that way as well. So 40, but since it's uniform, let's just divide it by 12. And I get 335.33. And each month should be my expected counts if it's uniform distributed, right? Okay, so let's do chi-square. Chi-square is the sum of the observed minus expected squared over expected. And if we go ahead and do the test, okay, Oh, do it on my calculator on the side. So I'm going to put in my list. So in list 1, I'm going to put my observed counts. So 321, 360. I'm just going to go down the list. 367, 383, 402, 329, 31, 354, 376, and 355. And then L2 is my expected counts. And so that's going to be 335, 33. Just got to put that in 12 times. Okay, so stat test chi-square goodness of fit. Degrees of freedom 11, since there's 12 categories, one less. And I get chi-square is 46.79. That's a 4. And the p-value is 2.3 times 10 to the negative 6, which is 0.1, 2, 3, 4, 5, 6, 3. So that's pretty small. Okay, that's really small. In fact, so that's evidence for HA. So since the p-value is less than 5%, this is evidence that bursts are not spread uniformly across the year. And as you think about it, maybe that does make sense. Maybe there's more bursts 9 months after the wintertime. I don't know. You figure that out. Go from there. All right. See you. Bye.